Welcome to Unit 13, Video 4, Ideal Gases. By the end of this video, you should understand what an ideal gas is and the assumptions made in the ideal gas model. You should understand when and why real gases stop behaving like ideal gases. And you should be able to perform stoichiometric calculations using molar volume and the ideal gas equation. An ideal gas is a theoretical gas described perfectly by kinetic molecular theory. In other words, it's a gas that we kind of make up, that we can mathematically model with incredible precision. And it turns out that most real gases actually behave almost exactly like an ideal gas under most conditions. So we can actually use this theoretical ideal gas to do calculations about real gases, because real gases behave ideally most of the time. The ideal gas itself does not exist because we make two false assumptions when we mathematically model ideal gas behavior. First, we assume that gas molecules take up no space. If you look at the picture here in the bottom right-hand corner, the tiny little red dots spread throughout the orange area are the molecules themselves. The orange area represents the space between the molecules. Down here in the bottom corner of this picture, you see essentially the combined volume of all the particles themselves. Notice that the red square representing the combined volume of the actual particles is relatively small compared to the orange volume of the entire gas. Therefore, we say that the volume of the particles themselves is negligible. We say they take up no space. Another example would be if all of us in the entire class were to go to Yankee Stadium and spread ourselves out as far as we could all around Yankee Stadium. The volume of the stadium itself would be far, far greater than the volume occupied by our bodies alone. Therefore, we could say that the volume we occupy is negligible as compared to the entire volume of the stadium. We also assume that gas molecules do not attract each other. This is also a fair assumption since gas particles are so far away from each other that they actually don't really attract each other to any significant extent. Again, if we're all spread out at Yankee Stadium, it's very hard for us to interact with one another because we're so far apart. Again, these are false assumptions, but they actually work to allow us to mathematically model gases. PV equals nRT is the ideal gas law, or Pivnert. This describes the behavior of an ideal gas in terms of its pressure, volume, temperature, and number of moles. It's actually a combination of Charles' law, Boyle's law, and Avogadro's law that you learned at the very beginning of the year. In this law, P stands for pressure, V stands for volume, N is moles of gas, T is temperature, and R is the universal gas constant, which is 0.08206. You will be given this constant. You don't need to memorize it. This law will work as long as your temperatures are in Kelvin, your pressures are in ATM, and your volumes are in liters. Just a reminder of some conversions before we move on. Remember that to convert between ATM, torr, and millimeters of mercury, 760 torr is equal to 1 ATM. To convert to Kelvin from Celsius, you add 273 to the Celsius temperature, and to convert from milliliters to liters, you divide by 1,000. Here's some example problems to try. We'll do the first one together, then you can try the rest on your own. This first question asks how many moles of argon gas at 104 degrees Celsius would occupy a volume of 6.8 liters at a pressure of 270 millimeters of mercury. We know this is an ideal gas law question because it asks about moles and gives us pressure, volume, and temperature. So I'm going to start by writing our equation, PV equals nRT. Notice I'm given temperature in degrees Celsius, so I'm going to convert that to Kelvin by adding 273 to the Celsius temperature to get 377 Kelvin. I also need to convert my pressure from millimeters of mercury to torr, so I'm going to divide 270 by 760 to get 0.355 ATM. Now I have everything in the proper unit, so I can actually solve the problem. Plugging my pressure, 0.355, My volume, 6.8. I don't know my moles, so that's N. Ideal gas constant, R. And T, 377. I can solve for N. Solving this equation, I find that I have 0.079 moles of argon. Pause the video here and try the next two on your own. When you return, I'll reveal the answers.
Welcome back. Here's what you should have gotten.
As we mentioned before, ideal gas law makes some very important false assumptions. These false assumptions don't really matter under most conditions. But notice, real gases do deviate from ideal behavior under certain conditions. A real gas will stop behaving ideally at low temperatures and high pressure. This should make sense. Consider the picture below. Notice that at a high pressure, the volume is much, much smaller. Therefore, the volume of the gas particles themselves begins to become much more significant. Again, imagine that we're all at Yankee Stadium, but now instead of all being spread out throughout the stadium, we've all crammed into one elevator. Now the volume of our bodies is much more significant as compared to the space in the elevator. Luckily, we don't do much work at low temperatures and high pressures, so this won't really affect our calculations in any significant way. But it's important to note that if you're working at very high pressures and very low temperatures, real gases do deviate from ideal behavior. Here we've graphed the relationship between PV over RT versus P. For an ideal gas, represented by the dotted line, this relationship should equal 1. Notice that these gases deviate quite significantly from ideal behavior. However, look at the pressure scale here. It goes all the way up to 1,000 atm. The little box at the left shows a blow-up of 0 to 2 atm. Notice that between 0 and 2 atm, the gases hardly deviate at all. Particularly from 0 to 1 atm, there's nearly no deviation from ideal behavior. Since we almost always work at pressures of about 1 atm, this means that the ideal gas law works just fine for all the gases we deal with. It's also interesting to consider why certain gases deviate more than others. Notice CO2 deviates the most, whereas H2 and N2 deviate quite a bit less. Consider the assumption about the attractions between molecules. CO2 has stronger intermolecular forces than H2 or N2 due to the fact that it has more electrons. Therefore, its dispersion forces will be stronger, which causes it to deviate more because it disobeys the assumption that particles do not attract each other. Consider the math we've been doing using PV equals nRT. Notice that at no point do we take mass or identity of the gas into consideration, only its pressure, volume, temperature, and moles. Notice that if volume, pressure, and temperature are all the same, as they are in the picture at the bottom, we'll always get the same number of gas molecules, or the same number of moles of gas. Even though the masses will be different because the mass of each individual particle is different, in our PV equals nRT calculations, we will always get the same number of moles given the same volume, pressure, and temperature. This allows us to define the concept of molar volume. According to the assumptions of the ideal gas law, 1 mole of any gas will occupy 22.4 liters at STP, standard temperature and pressure. Recall that standard temperature is 273 Kelvin and standard pressure is 1 atm. This means that no matter what gas you have, as long as it's at 273 Kelvin and 1 atm, 1 mole of that gas will occupy 22.4 liters. Just like we used molar mass to convert between mass of a substance and its number of moles, we can use molar volume to convert between volume of a gas and the number of moles. We can use molar volume and PV equals nRT to perform stoichiometric calculations using gas volume. Here's a sample problem. Let's look at number 1 together, then you can pause the video and try the rest on your own. Like any stoichiometry problem, I have to start by balancing my equation, which I've just done. Looking at number 1, I'm asked what volume of NH3 will be produced by the complete reaction of 12.5 liters of H2 at STP. Since it's at STP, I can use molar volume and I don't have to use Pivner. Just like a mass-to-mass problem, I need to start by converting what I'm given into moles. In this case, since it's 12.5 liters at STP, I can convert by dividing by 22.4 moles per liter, or molar volume. This gives me 0.558 moles of H2. Now, using my balanced equation, I set up a mole ratio. I know from the equation that 3 moles of H2 will produce 2 moles of NH3. So 0.558 moles of H2 will produce X moles of NH3. Solving for X, and I find that we get 0.372 moles of NH3. Again, like a mass-to-mass problem, I want to convert these moles back into, in this case, volume of gas. So since I'm at STP, I can multiply by molar volume, 22.4 moles per liter, and I find that this reaction will produce 8.33 liters of NH3 gas. Pause the video here and try the next two on your own. Notice in number 3, you start at STP, so you can use molar volume for your conversion of N2 to moles, but your conversion of H2 to moles will have to use Pivner, since you're at non-standard conditions. When you come back, I'll reveal the answers.
Welcome back. Here's what you should have gotten.
That brings us to the end of this video. Let's review our goals. First, we looked at what an ideal gas is and the assumptions we make for the ideal gas model. Then we looked at when and why real gases stop behaving like ideal gases, when our assumptions that the particles take up no space and exert no attractive forces on each other break down. This happens at high pressures and low temperatures. Then we performed calculations using the ideal gas equation, PV equals nRT. Then we performed stoichiometric calculations using molar volume and PV equals nRT when we were not at standard conditions.